Welcome. This is the launch of Aivia 6. My name is Luciano Lucas, and together with me I have Chi.
Hello.
And Sean.
Hi.
We're introducing a really cool release of our flagship product, Aivia. We've been working on it for 4.5 months for this particular release, and Chi here is going to be talking about one of the major features, which is the 3D EM image segmentation using deep learning. And we think this is the first one commercially available. And Sean is then later going to talk about our new volume rendering tool that is able to render in real time extremely large images. All right, so the main two features we're going to be talking about today are the 3D EM image segmentation, which I have some images here. This middle one doesn't look like EM. That's a confidence map created from our deep learning model. And we're going to be talking about this new volume rendering engine, which uses multi-res, multi-block technology. And Sean is going to talk about that in a moment. So deep learning for semantic image segmentation has become pretty popular in the last 5 years. A lot of people have used it and they don't even know it, like in Facebook or in Google searches and things like that. It's already there. It already does a job for you. And if you're lucky to have a Tesla, it definitely does a job for you because it's identifying obstacles on the road. So in the last 40 years, there's been quite a lot of development. These are the key people that you will come across when you start to search. And there's several fields where you will find applications for deep learning. I have a few listed down there, but there's probably even more. And I'll put this presentation online so you can use those links that I have down there. Speech recognition is probably one that a lot of people would use also on their smartphones. If you use Siri or Cortana or anything like that, it is translating your speech into text and into actions sometimes. And that also uses deep learning. And if we have a look at some of the earlier publications, this is even preprint, you can see that the rise in publications is pretty obvious. And here the authors broke it down into the types of deep learning networks that people are applying, and also the types of structures that they are trying to detect. So segmentation seems to be still the highest number of people are trying to do segmentation, but some detection, some classification, and even some registration down below here. The type of microscopy or the type of imaging isn't just the type of microscopy or imaging that we do. Typically, I guess a lot of you will be doing light microscopy or electron microscopy, so that would be under this category. But actually most people using this type of technology are in the clinical setting, so they are using MRIs, CTs, and so on. And it's not surprising because, of course, those fields tend to be a little bit ahead when it comes to use of this kind of technology. In this case, they certainly are. So there is still a lot for us to catch up, I think. And the trend is obviously it's increasing, or the number of papers is increasing, so the trend is upwards. If we look at a couple of applications, I don't want to go into a lot of them. There's really a lot of them that we could cover, but if we look at a couple of them, here on the right hand side I have one that shows the increase in resolution. That's a pretty interesting concept. I haven't seen this used yet in confocal microscopy, but I'm sure somebody has done it already or is planning to do it to increase the resolution of images purely using deep learning. And in this example, they didn't use fluorescence microscopy, but still the principle is the same. And on the example on the bottom, it's actually the first example I could find that shows deep learning being used for the segmentation of electron microscopy images, and that dates back 7 years. Since then, quite a few other people have started to use this type of technology for the segmentation of really hard data sets. like EM images, they tend to be a lot harder to segment correctly in comparison to fluorescence microscopy images. And that's probably one of the reasons why researchers have, in this field, the field of connectomics, they started to use deep learning to explore the possibilities, because it's definitely showing some good results. So machine learning and deep learning with microscopy, you can see the deep learning trend is definitely increasing here, and machine learning in volume is higher, but it doesn't seem to be increasing as much, unless in the last few months of this year there will be a lot of publications. In any case, both of them are increasing, but we're still very, very far away from the leaders, which are in the financial market. There, just in 2016, there were almost 28,000 publications in this field, and they don't even publish that much typically. So this is probably an underrepresentation of the use of machine and deep learning in the financial market. I think we are just at the beginning of this, of the use of deep learning for analysis or segmentation of microscopy images. And we're very excited to today share with you some of those benefits, and hopefully you'll try it and you will like to use it. Before us, however, there are quite a lot of people doing this kind of work, and they're doing amazing work. You should check at least these people. There's even more, but these guys are amazing. The labs that they lead are doing incredible work in the field of connectomics, and you probably have seen them at conferences presenting keynote speeches and blowing everybody's mind away with the EM reconstructions they are able to create. They are leveraging quite often in those presentations. They're leveraging machine learning and deep learning, specifically convolution neural networks, which is what we are using. Unsupervised model, you would start with a network of some sort, can have different architecture. You feed in lots of images, and the first layer here, the first hidden layer, normally there's more than two in order for it to be considered a deep network. The first layer here can identify through convolution with a filter that goes through the whole image in detail. It will identify small features. The second layer, the hope is that the features become bigger and start to be more understandable if we could look at them. And the third layer should have faces that will not look exactly like the input, but because they are artificially created, but they should look like faces. So in the end, for an unsupervised learning model like this, you would end up with a network or a tool that can detect faces in a picture. So if you feed a picture with faces, it should know that there are faces there, and depending on the type of network, it might tell you also what the area of that face is, and so on. What we are using is supervised learning because we're providing ground truth together with the raw data, and it's a similar principle, but with some adjustments. So we start by putting in a raw image, not a picture of a lady, but the picture of electron microscope, and a picture of a brain sample taken with an electron microscope. We feed that in, and we provide a lot of ground truth, or some ground truth. In this case, it's actually a very small amount, and you will hear about that in a moment. And we run the network so that it finds the error in comparison to the ground truth, and then we use backpropagation to adjust the weights and biases on these networks so that this network can correctly detect which of these people it is. So if this picture is of Anna, let's say that's a picture of Anna, we would teach with many pictures of Anna, and by doing that, we would train this network to identify Anna in a picture. So if we are to provide different pictures of her dressed up in different ways, you are going to be able to automatically identify her. In the case of Aivia 6, what we've trained the network to do is to identify the cell membranes. So we started out with cell membrane raw images over here. we provided plenty of masks that identify areas that have a cell membrane or that don't have a cell membrane. Either works fine. And in the end, we have a network that can detect cells and the cell membrane. Okay, so I'm pretty much done with this part. So each each cell is labeled in what you will see in the demo in a moment. Is that each cell will be labeled in a Z slice. So this is a raw image. This is what you'll see in Aivia, and you can go up and down. Typically, this is very time consuming. If it's done manually, it can take months for a single cell. If it's a very large cell, it can take weeks to months to manually draw, and requires a lot of manual work and highly skilled manual work. Typically, this has to be done by a couple of people so that you can compare variability between the two human users. In Aivia, thankfully, you just hit a button and it will take the input and create an output like this, and it will also create a mesh. So with that, I will pause and let Chi come and join me here.
Hi, my name is Chi. I'm the application software manager at DR Vision, and I'm proud to introduce the brand new feature of Aivia 6. That's the automatic segmentation of neuron tissues in 3D EM images using deep learning. And it's well known that the deep learning models outperform many of the traditional image processing based algorithms in the scientific competition. And we are proud to introduce this tool to use deep learning for 3D EM segmentation. I'd just like to briefly introduce the technology behind this tool. And first, our deep learning module start with offline deep learning training using UNet architecture, which is excellent for image pixel-wise segmentation. And we train on 3 public dataset with manually created annotation to generate trained deep learning model. And when we apply the deep learning model in Aivia, first the trained model will be loaded in onto Aivia and become a Aivia recipe, and then we apply the recipe on the 3D image stack to generate 2D confidence maps. And from the 2D confidence map, we reconstructed the neural tissues in 3D. You can see the 3D reconstruction mesh on the right lower corner. And then I'd like to briefly introduce the deep learning architecture in Aivia 6. Aivia 6 uses UNet with densely connected blocks. And it's well known that UNet architecture is a conventional architecture for fast and precise segmentation of images. And the deep learning architecture with encoder and there are skip connection between the encoder and decoder. And the encoder on the left, it tries to downsample the data and to the fewer and fewer data. And then the decoder on the right will upsample data until it has the same resolution of the input image. Traditional deep learning architecture may only have the decoder part of the UNet. So some application to classify image to find to classify an object into a category may only have the decoder part of UNet, but it is not suitable for image segmentation. With the decoder, the UNet is capable to generate outputs with the same size of the input image and perform pixel-wise classification. That makes it suitable for the EM segmentation. And we also adapted DenseNet into the UNet. DenseNet is a state-of-the-art. It was just introduced this year, and it has significant less parameter required in each layer, and that makes it more trainable and generate even better segmentation result. So in Aivia 6, we implemented the UNet with DenseNet together and to train the model. And there are some detail about the deep learning training performed to generate the UNet model that will be used in Aivia 6. So the model was trained with TensorFlow and Keras script on a single NVIDIA GeForce GTX 1080 Ti GPU. The average training time is about 7 hours, and the deep learning model contains about 800,000 trainable parameters. And the weighted binary cross entropy loss function was used for the segmentation purpose, and the Adam optimizer was used to minimize the cross entropy loss function. And the input image were augmented on the fly during the training. This is to increase the effective size of the training data. So the augmentation may include the rotation, flip the image, elastic transformation, adding Poisson noise to make it more variety for the training and make the algorithm more robust for different variation of images. And just like to quickly show some screenshot of the segmentation result. On the left, they are input EM images, and in the middle, that's the confidence map created by the deep learning model we train on, and the brighter part represent the neuron tissues, and the darker part represent the boundary between the tissues. And the color image on the right is just the cross-section of the 3D reconstructed neuron tissues that you will see on the next slide. And then there are two 3D surface rendering images. On the left, this is all the segmented tissues rendered in one image, and the Aivia also allow you to visualize some selected neuron tissues. You can see the image on the right. Thank you for your attention, and Luciano is going to give you a live demo for the deep learning module.
The 3D EM analysis is the pre-trained deep learning model that Chi just showed, and we can set this up like that. So you would put in here the intensity threshold. So this is at the membrane, and subset filtering, so that you remove some small objects that you don't want, and then you hit go. So for one image like this, so this is 600 by 600 pixels, it takes about 30 seconds. And that's the same speed, so it scales linearly. If you have more images, it will just take 30 seconds per image. And that's why I'm not showing you a full stack, because it could take easily half an hour or an hour to run if you have a bigger data set. But still, if you compare that to manual segmentation, where it would take weeks or sometimes even months, depending on the complexity of the data set, the density, and also what kind of software you're using, of course, then it makes a lot of sense. It's just, you know, an hour or something like this versus weeks. So the result is here. You can see the outlines. That's what it looks like. So this is all done automatically, and we can zoom in to have a look at this. And the segmentation is perhaps not perfect, not 100%, but it's pretty close. And of course, we know that this isn't going to be perfect for everybody, and that's why, and I'll mention this again later, but that's why we will offer as a service to the people that have Aivia. So Aivia users will be able to send small samples of ground truth for their data, and we can update the model. And then give the model back that is more tuned to their type of data. And we can do that a couple of times to get to a good result. Also, it will be possible to edit these directly on the image. In case there's only small mistakes and you want to to edit them directly on the image, it will be possible to do that. But that's the kind of result you can get for a single slice. I will open here another image that has more slices. Actually, it's the same one, but that has been already processed. So this is a much bigger stack, and you can see I can play through that stack to look at different areas, and it is actually really for somebody, I've done a lot of manual image segmentation over the years. So this is really pleasurable to look at this, because I know how long that would take to create this kind of segmentation. So let's go to 3D. So that's what it looks like in 3D, where you can we can also remove some of these, so it's more easily understandable what we have segmented here. So you can see these are individual segments of the dendrites. This is a small crop, so you will only see small bits of the dendrites or the axons, depending on the results, depending on the region that you manage to capture. But that's the kind of results we can achieve already with relatively little training data, as you heard Chi explain. So with more data, we could of course get even better results. But the infrastructure is here, and it's deployed in a very stable manner. You don't have to install any other software. You can just have Aivia. It already comes with all the libraries. All you have to do is load your EM image in, apply the model, and enjoy the results, and enjoy the fact that you don't have to do all this manual segmentation. One thing I didn't mention is you do get to see the output from the deep learning model. This is the confidence map. That's what Chi also mentioned. So this is an intermediate step between the EM raw image and the full segmentation that we have here. You also get to see the confidence map. That's the raw output from the deep learning model. And basically, black means we're very confident that it's a membrane, and white means we're confident that it's a cell. And in some places, you can still see shadows of internal structures, because that's a very strong internal structure, very high contrast, so you still see them there, and sometimes that can mess up our segmentation. In this case it didn't, but it can, and so there is tuning to be done with additional small amount, but additional training data sets. When I say small, I mean maybe 4 or 5 regions of interest, each one of them 30 slices, 500 by 500 pixels, 30 slices, 4 or 5 of them with ground truth. That's a relatively small amount of training data that we can use to augment the model that we have already implemented, and that works reasonably well out of the box. Okay, so I think that's where I will pause oh yeah, one other thing. Let me see where I have that. It is possible in Aivia to look at all of these objects in here. So all of the objects that we have created, we can look them up here. This is our classification tool. So you can in fact classify these if you wish to, and use machine learning to classify them. But all I'm doing right now is show what did we detect and what is the general morphology of the things we have detected. And that helps understand whether we have some segmentation problem or if it's looking good. And in general, this is looking pretty good. Some of these are probably not correct. That's because we have segmented some that are on the edges of the frame, and on the edges they typically become cut and become round objects, whereas these long ones are the ones that are complete inside of the 3D structure, and then of course you get them all there. The future of Aivia with deep learning. There are a lot of networks. You can see them here. We don't aim to have them all implemented in Aivia. We will, however, continue to monitor what is published, and we see what is presented at conferences, and the best ones, the ones we can implement or re-implement ourselves and perform really, really well, we will then put them into Aivia and deploy them in future versions. We're going to be doing that not just for 3D EM images, but in general. If there are other applications out there, or if you would like to have an application, maybe you are developing one and you would like to have it into Aivia, we should talk about that. Aivia users, as I mentioned, if you are using Aivia and you want to do segmentation of EM images for now, you can send us small areas of ground truth and we will retrain the model for you here, which takes some hours, as you heard Chi explain, and we will send you the file back with the trained model that you can just apply in the same way that I applied it a moment ago. As you know, there's enormous demand for rendering of very large images. And during the summer, we were doing an Aivia summer tour. We went to a number of microscopy facilities across the country, East Coast, West Coast, and also in Madison. And everywhere we went, the same problem appeared, which is loading and rendering very large files quickly and with good quality. So we went back to the drawing board. Our volume rendering wasn't bad, but it wasn't high performance. So we had to implement something that allowed us to do real-time volume rendering of super large data sets. And now it's working, so we want to share it with you. And why is this even relevant? And what applications are people using for this? The main one, I would say, is the light sheet microscopy. It's not the only one, and perhaps you would disagree that this is the main one, but I think this is the one that is pushing the whole field forward. Lattice light sheet microscopy by Betzig and colleagues, of course, is one of the main ones. And that kind of technology creates all sorts of problems. We'll talk about those and how we have tried to address those. The other one is expansion microscopy. This is really an interesting one because, as you know from the work that Ed Boyden has published, it can expand the tissue, keeping the morphology. And this is really ideal for looking at small structures, but still using light microscopy, which most of the time is easier to use than electron microscopy. and tissue clearing techniques, which together with light sheet really make it, I would say it's a golden age for light microscopy, because you can finally image very large samples at high resolution without actually damaging them if you want to do it in live tissue. So it's a very exciting time. The file sizes can be multi-terabyte for a long time lapse. It's never multi-terabyte for a single time point. And that's an important distinction to make, because the volume rendering fails not because of the long time lapse. The long time lapse causes problems with memory management, but not really the volume rendering. And we'll talk a bit more about this. Typically, the volume rendering fails if a single frame is bigger than RAM or bigger than the GPU. That's when it fails. Anyway, we go back to that. So the volume rendering, or the images, are 500 gigabytes to 5 terabytes for light sheet. For expansion microscopy, they can be hundreds of gigabytes, but it's not very frequent. And it's a technique that is still expanding in its use. And then clearing techniques have already exploded, and there's a lot of people using it in dramatic fashion. And the datasets can be extremely large. 2 terabytes can happen quite easily, even more than that. And typically it's made up of stitched, lots of stitched 3D blocks. So when would you benefit from a high performance rendering engine like what we've put into Aivia? Well, as soon as a single time point doesn't fit into GPU memory, then you have a problem. Because until that point, if you can fit everything into GPU memory, that's the simplest way to do it. It's just to load it all there. Of course, it can still lag a little bit to move from time point to time point, but it's the simplest thing because you don't need to do anything intelligent or smart with your file. It can just be a single block file, and you put it all into the GPU and it's fine. However, a lot of these data sets are much, much greater than the best GPUs that you can use today. So the one we have is one of the best. It's a GTX 1080 Ti, and that only has 11 gigabytes. And any data set bigger than that, and basically you wouldn't be able to load it. So you need something intelligent, something smart, something that will make good use, the best use of your hardware. So what are the components that we have to play with? One is available GPU memory that I already mentioned. Then the memory management and the disk speed is another. And you need a high performance file format. Together, these three things work to give you the best flexibility. You can load quickly, render quickly, and move around quickly, even in a very large file that is much greater than in size than the GPU memory available. So this is the pipeline that we recommend. The recommendation that we have is to use our offline conversion tool. That's part of Aivia 6. It's also newly launched today. You can just drag and drop and save, and it will run in the background. So you can have Aivia open, you can have the batch converter going in parallel. And once you have that file, what we've seen in our tests is that you can get the file back, no matter what the size of the file, you can get the file back to a rendering situation where you can see the data set and interact with it again within a few seconds. So first convert, then open Aivia, the Aivia TIFF, go to the 3D view, and pretty much within 10 seconds or less, is actually more, it's closer to 3 seconds, you can render the image interactively. And with that, I will pause and invite Sean to come and give us his view on the work that he's been doing together with Bryce and Chris. Thank you, Sean.
Thank you. Thanks, Luciano. That was great. All right. Hi, everybody. My name's Sean McElroy, and I'm one of the engineers here at DR Vision. We're working on Aivia 6 and the new rendering engine. Okay, so, you know, one of the big problems, as Luciano said, was these really large data sets. And, you know, a naive approach would be just take your really big data set and, you know, downsample it. So you have a 30 or 50 gig data set, you can downsample it to 1 or 2 gigs and stick it on your, you know, consumer GPU that has maybe 4 gigs and view it just fine. But that'll look really terrible. Or you can cut off pieces like slices or cut out chunks and just look at those pieces, and that also works. But that's not quite ideal. So instead, what we aim for in this release is, you open the file, and as he said, you can offline convert your file, or you can just load it directly. It'll also convert on the fly the necessary resolutions that it needs. And basically, the first step is to take your file, and depending on the dimensions and the relative ratios of the time frame, it'll cut your file into a nice geometry that is between 1 and around 80 blocks for multi-block software. And so the other important thing is it'll cut it up, and it'll determine based upon where you're looking in Aivia while you're looking around. If you move the camera left to right or whatever, it'll decide, oh, that block, that should be high resolution because that's what they care about. And these over here, they're behind you or something, we don't really care, so we won't upsample those at all. And you can sort of get the idea of where we're going here, right? So then you can go to the asynchronous texture loader, and in parallel, this will be running, and as the block layout manager makes decisions every second or every sub-second as it goes, the texture loader will say, oh, we need this one loaded here, oh, we need that one loaded there. And it streams over an OpenGL pixel buffer technology, which lets us stream the data to the GPU without really impacting whatever else is going on the CPU, which basically means you can run recipes or move the camera around or whatever it is. More traditional approaches would be when you load the GPU with your data or whatever data, it sort of halts all the processing and you wait. But here we do it asynchronously in the background. So on the GPU here at the bottom, you just build up more and more texture blocks. And so for a given position in your data, say you have the block at the first block, we'll call it block 1. You might have a really low resolution version and a higher resolution version. It's sort of similar to how Google Maps works, right? You zoom in Google Maps, and you have the house, but it doesn't show you the rest of the world. And if you zoom out, you can't really see the house anymore. So similar to that, you load all these blocks onto the GPU, and then our rendering engine using VTK will manage these in the background in parallel, taking the input from the block layout manager here and render them using the ray trace renderer. And the ray trace renderer makes everything look really nice and fancy, and it renders at a very good performance because you're not actually rendering 80, 100, 200 gigs of data. You're just rendering enough to be able to know what's there and the stuff you're looking at. So it goes over here to the rear buffer, and it gets flipped over to the front buffer. Now you can see it, and there's a very parallel path here between the input going down this direction to the GPU and up to the rendering engine, and also straight to the rendering engine, such that in real time, as you move around the scene and you zoom in and you zoom out, it'll look and feel responsive while it's still streaming the textures in and out. Very similar to how a lot of the more advanced video games work, or again, Google Maps. And so, having said all that, what's the main advantage we got here? The main advantage is, for example, in these 5 test data sets, it's a lot faster. As Luciano said, it's basically just a few seconds to load the data, whereas data set A here was almost 30 gigs, including the 11 time points. It used to take 30 seconds to load the data, and you would just sit there and wait. But now it takes 4 seconds, and even during those 4 seconds, you can still do things. And after the 4 seconds are up for this data set, you'll be able to see the whole volume, or whatever your data set is you're looking at. And so a more interesting data set might be number 2B here, and this one was 2000, I don't know if you can read this, but it's 2000 by 2500 by 1500, so fairly large, and it was 1 time point, 1 channel, so not cheating in any way like that, and still 16 gigs. So a naive approach or a previous approach would have to have downsampled this at least by 2, roughly. But with the new Aivia 6 rendering engine, you'll be able to see all the detail as you look at it. And by that I mean you look around the scene. So probably the most interesting data set here is E, and this data set was, or is, almost 10,000 by 12,000 by 700, and it's 1 time frame. And so if you load all 3 channels, that's loading 230 gigs, And obviously that's not going to fit, and if you were to downsample it, it would be, you know, the size of a postage stamp or something. So basically it would never finish, or you'd get worthless data to look at. But with the new approach here, we can render the whole thing and show you the actual details for what you're actually looking at. So I hope that gave a little bit of background into our rendering engine and sort of the flow of how the data actually gets off the file on your disk and streams over to the GPU so you can see it while not bogging down or, you know, being slow.
So that's 40 gigabytes, and it's there. So that's less than 3 seconds, and we can start to interact with the data set. And if you zoom in very quickly, you might get a chance to see that you don't have the full res yet. And if you are wait a little bit, you start to get all the details. You can see there in the background those very fine structures, and actually the whole view is updating to see the finest structures that this data set can offer. We have a few rendering modes which we have introduced in the past, but I wanted to show you that they also work well with the new volume rendering. So this is, I'm just going to change the colors here a little bit. Okay. Can render the inside if you prefer. I don't think I've ever shown that the lookup table can be optimized, can be adjusted. So I'll show it, take the opportunity to do that now. So it doesn't have to be a linear progression here on this line, which gives us the possibility to make some of the channels semi-transparent. So all of this time we're doing all of that hard work in the background that Sean was describing, of swapping in memory, getting you the higher res visible, the lower res to take it away, and it's pretty much seamless as we move around a data set of this size. So this is the type of performance we can get. Very large files loading extremely fast. Within 3 seconds or so you can get an Aivia TIFF visible, displayed, and interactive. And you can convert at a very fast pace, 5.8 gigabytes per minute. So I think that should help some of those microscopy facility sites that we visited during the summer. One important thing, the TIFFs that we do save, so our file format, can be opened by other TIFF readers. So ImageJ or any other software that can read a TIFF will be able to read this directly. And that's because we're keeping a full res image available inside of that Aivia TIFF, so that it stays, continues to be easy for you to open your data in any other software that you might need to use. All right, so we're almost at the end. Just wanted to recap the kind of functionality that we now have in Aivia. This is the full portfolio. We can do visualization both on the screen, like a desktop screen, or in VR. We have a lot of applications, image analysis recipes or pipelines for 2D image analysis and 2D plus time. We've added the 3D object count during this year, and actually with Aivia 6 there's a major upgrade in that algorithm, and also in the options that you have there, including several previews and multiple options for splitting objects that are touching, so cells that are touching. There's a lot of new functionality. I didn't get to demo that today because we really wanted to give you enough time with the 3D EM and the new volume rendering, but do check it out. You can download the software and try it for yourself. We have the 3D neuron analysis that we launched a year ago, and we've been working on during this whole year. The machine learning classifier that now works on everything apart from tracks, so everything static, I should say. So 2D objects, 3D objects, and neurons works on all of those. And of course, we continue to optimize the GUI and the performance. In this case, we optimize the performance for large data volume rendering. Here's a slightly more detailed list of features that we're launching today. We talked primarily about the first two. I mentioned the 3D object detection. We've also added something more to our machine learning classifier tool, and it's called novelty detection. This is used when you teach a couple of classes or more classes and then ask the software if there are potentially other classes of objects, other phenotypes that you have not identified. And so Aivia will be able to tell you what's the likelihood of having a third class of objects, or a fourth depending on how many you classified, but an additional class of objects or additional class of phenotypes in your images that you have not taught on. And I think all the other ones we have measured. Perhaps I should give a shout out to John and Casey that have also worked very, very hard, but on many, many, many areas of the software. So it's harder to tell a specific one, but I can tell this one. So John was working on the background measurements, and Casey has worked on pretty much everything to do with the GUI, and there's quite a few improvements as well. So I think I'll finish there. I'll ask Chi and Sean to come and join me. So I think that's pretty much it. I wanted to thank everybody for joining, and for Chi and Sean for their presentations today. I do recommend you go get your trial license at drvtechnologies.com and then /Aivia6. You will find there a link to download or to request the download for Aivia 6, and we'll be happy to send you a license so you can test it out. So thank you so much for joining the launch of Aivia 6. It's been a pleasure to be with you. Thank you, and see you around.
Thank you.
Bye-bye.
Bye-bye.